reminders, and I'm going to talk about what we're going to do today. Hey, and we're live. We're live for the 0 people that are there, but it still works. Ladies and gentlemen, today is probably going to be the first kind of note-heavy-ish day that we're going to be doing in terms of topics that I'm going to be teaching you. It's kind of a reteaching based on previous information, but we'll get there when we get there. As I said before, a reminder, make sure you've done your online textbook because I'm going to be assigning stuff next week. And please make sure that you got that benchmark done. The benchmark. Again, please try your best, as that information is stuff that we have not taught yet. So it's going to be a lot of like, I don't know how to do that. I don't know how to do that. I don't know how to do that. Try your best. Just try your best. I think so far out of the people who have taken it, I think like the average score is like 30% or something like that. Again, it doesn't count, but try your best is all I ask. Anywho's, here we are in Algebra 2. Fun fact, how many months are there in the school year? 10? It was 10. You're off for July and August. 10 months in the school year. You ready? As of today, you are 5% done with the year. I know. It's going to fly by, or it's going to go by really slow. I don't really care. I'm going to be still doing my thing and getting paid, so whatever. Anyway, ladies and gentlemen, this is the first note-heavy day. I'm just going to jump right into it. It's going to be phenomenal. It's going to be so phenomenal. I'm going to need, if you do not already have them out, I'm going to need those notebooks out and open. What's very interesting, and I'm going to say this out loud to all of you right now. The other day, I asked for the notebooks to be out and open in my A-Day class. And 3 or 4 students sat there and did nothing. And I'm like, huh. And I let it go for a moment. I'm just like, I wonder what's going to happen. And then I kind of said it again. I'm like, hey, and then, I thought to myself, self, what's going on here? And so I went to the first kid and I'm like, what's the deal? He said, I don't have a notebook. And I'm like, you don't have a notebook? That's interesting. Hold on. Hold that thought. Let's see who's in trouble. Mr. Murphy's room. Yes? Yes. You know where the stat button is? If you go into stat edit, you can enter in all your data. And then after you've entered in all your data, if you hit stat and tab over to calc and then run a 1-bar stat, it should give you those summary statistics. I can be able to show you. I'm in the middle of a class right now, but yeah. All right. Okay. Bye-bye. Why are people calling me? Whenever a teacher has a problem with mathematics or statistics in the school, they call me. Gosh. I make it all up. Everything here that I'm going to teach you today is made up. I'm just saying, like, seriously, it's all made up. You're going to find out next year. You're going to be like, oh, yeah, Mr. Markey, all that stuff is fake. You'll be like, then why did I learn it? I'm like, I don't know. Why'd you learn it? Anyway, so let's go back to my story. So the student was like, oh, I don't have a notebook. And I looked at the other 4 kids. I'm like, you get same with you? They're like, yeah, we don't have notebooks. I'm like, okay, why didn't you say anything? You could have told me. You know why? Open up that cabinet. No. Left. There you go. Both of them. You need a notebook? Take a notebook. That's yours. You need a notebook? Take a notebook. Yes, please, take a notebook. Dude, I have the stuff for you guys. I have it. You need a pencil? You need an eraser? You need tape? You need tissues and hand sanitizer for some reason? I don't know. You need a notebook? You need a binder? You guys need a binder? Anybody? Okay, I'm just saying, if you do, ask me. I will willingly give you guys this stuff. I want to. I need you to have it. Anyway, I steal most of it. No, every teacher gets a budget. Every teacher gets a budget, and I spend my money on this kind of stuff. The binders, though, I don't spend my money really on the binders for students. I actually recycle other students' old binders who leave them in my class. I'm serious. Here, open up that thing again. Open up the thing again. I just want to show you. It's pretty funny. Is it there? The one on the right, those are old notebooks. Not those. No, yeah, those are the old notebooks. Yeah, close that, and go to the cabinet to the right. There you go, top shelf. Those are old student binders. I only keep the ones that work. All right, that's fine. Yeah, she graduated like 4 years ago. Anyway, back to me. Ladies and gentlemen, in terms of notes, I started a little bit of notes last week, but this is the first official real-time taking notes in this particular class. So here we go. Typically, when I give you notes, I'm going to give you a date and a title. I'm going to expect that you keep an organized notebook. Keep an organized notebook. I'm calling this Reintroduction to Quadratics and Factoring. It's a reintroduction to quadratics and factoring. I say reintroduction because you have been taught this before. Do you remember that class that you stopped paying attention in near the end of the year, Algebra 1? Yeah, you know what I'm talking about. At some point, they tried to teach you quadratics and factoring. And you're like, what? Like, yeah, they did. They really did. But I'm here to reintroduce this stuff to you. Now, some of you may remember. Some of you may know how to factor. Some of you may have been taught how to factor in previous classes. And I'm going to be showing you something today where you're going to be like, Mr. Markey, I already know how to factor. I don't want to learn your way of factoring. That's fine. I'm not going to force you to learn my way of factoring. If you want to stick to your version of factoring, as long as you are correct and as long as you can show me your work, we're good. We're good. I'm not going to change the way that you learn something if you prefer it that way. But I do ask that you give my version a chance because you might like mine better. Let's talk about the basics of factoring, the basic idea of factoring. Let me try a number. 48. Back in like middle school, maybe even like 5th grade, I don't know. You guys did like factor trees? Yeah, factor trees, where you took like 48 and you're like, I got to break 48 up. Give me two numbers that multiplied 48. Sure. Can you break it down farther? Okay, yeah, of course you can. 6 goes to become what, 3 and 2. 8 becomes 4 and 2. And then the 4 becomes 2 and 2. Happy day. We have successfully factored. Hey, how come you don't use 1? Can I break down that 3 to be a 1 and a 3? What's the smallest prime number? It's 2. 1 doesn't count as a prime number. It doesn't. If it did, you'd be, as you just said, you'd be going forever. Can't do it. 1's not a prime number. 1 doesn't count. This was called prime factorization, in which the 48 was equal to 2 times 2 times 2 times 2 times 3. And these numbers were what we called the factors. Mathematics can be a violent sport. Yes, mathematics can be a sport, but it can be a violent sport. The idea of factoring is taking a number or a concept or an equation or something along those lines and literally ripping it apart into its prime factors. You guys did Legos when you were kids, right? I was very OCD about Legos, very OCD, which means when I put my Legos away, and yes, I actually put my Legos away. When I put my Legos away when I was a kid, no 2 Legos could be connected. They couldn't. I needed to break them apart before they went back into the box. I had to. That was my little OCD about Legos. But that breaking apart of Legos is this general idea of factoring. Here's 48. It's a combination of Legos. It's a combination of the Legos 2, 2, 2, 2, and 3. And in order for me to put them away, I have to break them apart into its prime Legos, or its prime factors, I should say. It's a weird concept. It's something that you've done with equations in the past. It's something that you have done with equations in the past, whether you believe it or not. There's a reason why we need to talk about factoring and quadratics, because it's going to play a major role in this chapter moving forward. A major role in this chapter moving forward. Let me remind you what a quadratic looks like. That is an example of a quadratic. A quadratic is an equation or expression that has a variable squared in it. It doesn't have an exponent larger than 2. Typically, a quadratic is going to be in a certain form, ax squared plus bx plus c, which I am going to write down in a little bit. This person says they feel like they're the only one in the stream. Are you signed in with your real name? Because literally the name is like Cryptify. I'm like, Cryptify. I don't think that's a real name. Anyway. But these equations do a lot of things. If I were to graph this, does anyone remember what the graphs look like? You do? What do they look like? Like a what? It is like a U. Yeah. They are U-shaped things. Do you remember the name of the U-shaped thing? Say it again. Parabola. Parabola. But it's a parabola. Watch this. If it'll focus. There's my equation. X squared plus x minus 6. If I graphed it, chapow! There's your parabola. It is U-shaped. At the bottom, it has a vertex. Parabolas could either open up or they can open down. Here's a parabola that opens down. Chapow. That's just what they do. Now, parabolas typically, if they do cross the x-axis, they typically cross the x-axis in like 2 different locations. And that is going to be a vital piece of information moving forward. Ooh, especially next week. Next week, we are going to be solving these quadratics. Today, I'm just focused on factoring. Now, some of you know how to factor. Good for you. Some of you don't remember how to factor. Okay, I'll get you there. Don't worry. But let me just show you a demonstration right here. If I were to take this quadratic and do a factor tree, again, like I did to the number 48, I could do a factor tree to the number 48, and I could break it down into its prime Legos. I could break this quadratic into its prime factors. The idea is that this quadratic could be broken apart into x plus 3 and x minus 2. Now, some of you are like, how did I do that? Oh, I got people in the chat. Hold on. It will let me change it. Oh, there he is and changed it. People are saying hi in the chat. He's talking about parabolas or however you spell it. Ew. I could have been in class right now. Oh, was she the one that broke her leg? Was Emily the one who broke her leg?
I was the one who was messaging her in the chat.
Yeah, that's what I'm saying. Was it her? Oh, no. Was it somebody else? Am I mixing you up with someone else? Again, I have like 4 different cohorts of Algebra 2. I'm still trying to get everybody straight. Oh, okay. I can see. Hey. Nice. All right, cool. Back to this. Oh, goodness. I can see the chat there. I can also see the chat over here. I just figured I was up here anyway. So anyway, but yeah, this can be broken down to its prime factors. Now, again, you're like, Mr. Markey, how in the heck did you do that? I'm going to explain. Don't you worry. I will explain everything. But first, let me make sure that this is right. If I'm right, I need to check to make sure that I'm right. And I'm going to multiply these 2 factors together. Some of you guys may remember how to multiply factors together. And that's great if you remember how to do that kind of stuff. If you remember how to do that kind of stuff, I should say. Do you guys ever learn FOIL? Cool. Remember what FOIL stands for? That's okay. That's fine. FOIL stands for first, outer, inner, last. I don't like FOIL. I don't like FOIL. I'm not a fan of FOIL. Hurts my teeth. Don't like it. You ever tried to chew FOIL? I mean, it hurts. But I'm going to teach you something slightly different. You ever learn lattice? Back in elementary school, did nobody learn lattice?
I believe I remember it.
It's dumb. It's so dumb. But it does help here. The reason why it helps here is for organizing, multiplying these terms together. Mr. Markey, that looks like FOIL. I know. I don't like FOIL. But what I'm showing you here will work no matter what, and it's a good organizational tool as well. I'm going to multiply these two things back together. I'm going to show you exactly what I did and what the concept is that we're learning today. If I multiply within the box, x times x is x squared, 3 times x is 3x, negative 2 times x is negative 2x, negative 2 times 3 is negative 6. And then, if I combine like terms, I get an x squared. What's a 3x plus a negative 2x if I added those two together? Ooh, positive x, and then minus 6. Did I end up back where I started? Absolutely. The general concept of what we're doing today is this. Go ahead. Ask it anyway.
I was going to ask it just to check, but you literally wrote up there. It's just to check.
Yes, exactly. No, here's the idea now. Sorry, just who chose FOIL? Sorry, I'm seeing the chat back and forth, but it's like it's a little bit faster here because then my phone picks it up like a few minutes later. It's weird. Anyway, and here's the idea. Factoring is the violent act of ripping things apart. You take the number 48, you rip that thing apart into its prime factors. You take this quadratic, you rip it apart into its prime factors. But then multiplying is the act of putting things back together. For example, if I go back here to the number 48, these are the prime factors. But what would happen? What would happen if I decided to multiply these back together? What would I get? 48. You don't have to guess. It's 48. 2 times 2 is 4. Times 2 is 8. 8 times 2 is 16. 16 times 3 is 48. Multiplying them back together ends up back where you started. Factoring rips them apart to their prime factors. Oh, that's wonderful. Prime numbers are the best. So, let me give you a statement and let me show you where we're going with this because, ladies and gentlemen, I'm about to get to the Tucker method. Anyone ever learned the Tucker method? Tucker method? Okay, whatever. Factoring quadratics is, quote, breaking down equations into its prime factors. Now, these prime factors are going to be very, very important moving forward because, ladies and gentlemen, these prime factors are going to allow us to solve quadratics. Not again, to give you a bunch of you like PTSD or some junk like that, but not only to solve basic equations like the one I just showed you, but also to solve word problems. Let the dread wash over you when you hear the phrase word problems. Here's an example. X squared, not of a word problem. X squared plus 7x minus 18. I want to walk you through the Tucker method. Now, I have not shown you what the Tucker method is. I have not talked to you about the individual steps of the Tucker method. Instead, I'm going to walk you through the Tucker method, and afterwards, I'm going to show you how I did it. Now, first and foremost, there is a certain step to the Tucker method. Step 1, which I'm going to skip because I don't need to do it for this particular problem. You'll see eventually. But then I move on to step 2. I move on to step 2, where I multiply these two numbers together. A times C. Mr. Markey, what the heck is A and what the heck is C? I'm going to tell you, don't worry. Don't worry. Just be patient and be calm. Negative 18. Hey, give me two numbers, any two numbers that multiply to negative 18. Any two numbers that multiply to negative 18. Any two. Go ahead. 9 and negative 2. Give me another two numbers that multiply to negative 18. Because there are technically 6 different examples you could give me. Go ahead. Negative 6 and 3. Give me another one. 6 and negative 3. Switch the negative. Yes. Give me another one. You said 9 and negative 2, right? Negative 9, positive 2. Give me another one. 18 times negative 1. People forget 1. People forget that you could do 1. 18 and negative 1. And of course, negative 18 and positive 1. There are 6 different examples that you could do. 6 different ones. But the first one that you gave me was correct. There's only one pair of numbers that will work. Mr. Markey, how do they work? Why do they work? Don't worry. Take a breath. I'm going to teach you how to do it in a little bit. Let's see. I'm going to throw these two numbers into the bottom of what I call a T-chart. And in the top of that T-chart, I'm going to put a 1x and a 1x. And Mr. Markey, why? Again, I'll show you in a little bit. Don't worry. I'm walking you through what the Tucker method is, and then I'm going to explain to you how it works. Ultimately, I end up with these two factors. Move that up a little bit. There we go. This is the factored form of the quadratic. This is the factored form of the quadratic. Now, this Tucker method, again, without having had explained it, having not had explained it just yet, the Tucker method doesn't take a lot of writing. It doesn't. It really, really doesn't. Once you get the hang of what the Tucker method is and how it works, you might like it way more than whatever method you learned in the past in terms of factoring quadratics. It's quite nice, quite simple, quite straightforward. I need to walk you through these steps. When you guys learned factoring back in like Algebra 1, did you, because I always try to ask this, did you guys learn it like where you had to do like an X or some junk like that? Right? Yeah, I don't like it. If you remember how to do it, that's fine. But if you remembered how to do it, by all means, do it. But I'm saying I don't like it. Somebody tried to explain it to me one time. They were like, an Algebra 1 teacher's like, oh, Mr. Markey, look at the X method of factoring. And they did it. And they're like, the students like it. It's so simple. It's so straightforward. And so I put an example on the board. I'm like, do it with that example. And they tried it, and it didn't work. And I said, so it doesn't work for that example, so you have to teach them another method. So they learned 2 methods? No. Did you ever have to learn formulas as well for factoring? When I mean formulas, I mean something like this. Like, did you ever have to learn like a squared minus b squared equals a minus b times a plus b? Okay, if you did, I'm not going to teach you that formula. Did you ever have to learn a squared plus 2ab plus b squared equals a plus b, the whole thing squared? If you did, you don't have to learn that from me. because the Tucker method takes care of all of that. It's so nice. The Tucker method works. It just works. It's so wonderful. So let's walk through what the Tucker method actually is. Who is this Tucker that I speak of? I don't know. Just some guy. Let's see. So, steps for Tucker method. Again, the Tucker method is specific to factoring quadratics. It is very specific towards factoring quadratics. That is what it is meant for. That is what it does. Step number 1. 3 letters. G, C, F. Some of you may know what GCF is and what it stands for. What is it? They stole it from you. They stole it from you. I know they did. That's okay. What's the key word there, though? The last one. Factor. This whole idea is factoring. GCF is greatest common factor. The first step of the Tucker method is to take out, to divide out, to factor out a common term in order to continue with the problem. Most of the time, the common term is just going to be a 1, and then you don't do anything. You'll see that in the next example. Step 2. Step 2 is to multiply A times C. Now again, where did A times C come from? A times C came from the following equation. AX squared plus BX plus C. There we go. This is the common form of a quadratic equation. Actually, it's standard form of a quadratic equation. The A is typically with the x squared, the B is typically with the x, and the C is typically just sitting off by itself. So when I say A times C, I'm not talking about the variables, I'm talking about the coefficients. The coefficients of A and C. Step 3, magic numbers. Now, I call this magic numbers, but these magic numbers have to do a couple things at the same time. They have to do a couple things at the same time. These magic numbers have to multiply to AC and at the exact same moment. They have to add to B. They have to do both at the exact same time. That's why they call them magic numbers. Now, before, I asked you guys for 2 numbers that multiplied to negative 18. You said 9 and negative 2. She said negative 6 and 3. You said positive 6 and negative 3. You gave me 6 different examples for numbers that multiplied to negative 18. However, let's go back. Why did these 2 numbers, the numbers that I'm pointing to, why did these 2 numbers work? When you add them up. When you add them up, they equal 7, which is the middle term, the B value. That is why they work. Ha 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 ha. So, step 4. Step 4 is a little weird, but again, I'm going to walk you through it. It's the T-chart. You saw me draw the T-chart earlier. But it's also T-chart and simplify. There may come a time where you're able to simplify. And if you are able to simplify, you should. A lot of the times you're not gonna because you don't have to. But if you can, you must. And then finally, step 5, write the factors. Now here's the beauty of it. If you have a quadratic that you would like to factor, you just walk through these steps. Oh, yeah, I know. He's talking about the light right being right in the center. I'm going to move the paper around a little bit. See if that works a little better if I move it this way. I really hope. It may or may not work a little better. A little bit better. I know, still working on it. Anyway, if you have a quadratic and you want to factor it, you knock out this method. If you have to do anything else, if you have to solve, if you have to do something with the factors, that's something else entirely. The Tucker method is devoted to ripping apart the quadratic, to factoring it into its prime factors. What you do after that depends on what the problem is asking. But this is what it will do. Let's put it into action. Let's try an example here. Let's try the following with the Tucker method. Example. 2x squared plus 3x minus 5. Nice. 2x squared plus 3x minus 5. Now, what's going to happen? We're going to walk through every step of the Tucker method, every single one. Step number 1, GCF, greatest common factor. So I got to look at all 3 terms. I see a 2, I see a 3, I see a negative 5. Ooh, I also see x's. I see variables. The only time the variables are going to be your greatest common factor is if they are in common in all 3 terms. See, these 2 terms have an x in common, but this one does not. And since it doesn't, x can't be the GCF. 2, 3, and 5, what do they all have in common? 1. That's it. But if you divide by 1, what happens? Nothing. Just stays the same, right? So I skip step 1. You only do step 1 if you can. If you can do step 1, you must do step 1. But in this case, it's just 1, so move on to step 2. Step 2, a times c. A times c in this case is 2 times negative 5, which gives me a negative 10. Yeah. That's all there is to step 2. That's literally all step 2 is. So now, I need 2 magic numbers. That works. 5 and negative 2. 5 and negative 2 are my magic numbers because they multiply to give you negative 10, and at the exact same moment, they add up to 3. Oh, happy day. T-chart. Every time you do a T-chart, put your magic numbers right in the bottom. Now, here's the weird part. I mean, besides the fact that this is all made up. Fun fact, I tell you it's all made up, but would you have enough knowledge to be able to, prove to me whether it's real or not? Are you able to determine whether or not the mathematics that I'm teaching you is actual real mathematics or just made up off the top of my head? No? I don't know. That's all I'm asking. Y'all look panicked. Anyway, back to this. Before, in the previous T-chart, in the top, I put a 1x and a 1x. There's a reason why I did that. What's x times x? X squared. X plus x, yes, is 2x. X plus x is 2x, but x times x is x squared. I got you. It's a very common stumbling block. But that's why I did 1x and 1x, because 1x times 1x is just 1x squared. But here's the thing, 2x squared. 2x squared could be like 2x and x. Or it could be x and 2x. So which one do I do? Up here, do I write 2x and x or x and 2x? I don't know. You don't have to worry about it. You don't have to worry about it. The reason why you don't have to worry about which one you put where is this. This term, where that says 2x squared, that a value, that says 2. It's an a value of 2. Simply put, you're going to put a 2x in both. Well, Mr. Markey, why? You'll see. You put a 2x in both for the time being. Step 4. Step 4 says T-chart and what? Simplify, ladies and gentlemen. And in mathematics, what the heck is it that you simplify? When you hear the word simplify in mathematics, what the heck is it that you are trying to simplify? Like terms? Maybe. A problem? Maybe. Something more specific. What mathematical object would you have to simplify? Something that goes back to late elementary school, early middle school. Ooh. Starts with an FR, ends with an actions. You got it. Fractions are your friend. You know how I know? Starts with FR. Ladies and gentlemen, here's the deal. I don't see any fractions up here, do you? I don't see any fractions. Huh, what? Wait, say again? I did that on purpose, though. The textbook doesn't teach this. What I'm showing you. The textbook does not teach this. But yes, I want you to temporarily think of these as fractions. I want you to think of this as a 2 over 5. Does that simplify? No, so you leave it. You leave it. Does 2 over 2 simplify? Yes, it does. Leave the negative where it is. Leave the negative where it is. But what does 2 over 2 simplify to become? Just a 1, but make it a fraction. 2 over 2, keep it a fraction, reduce it. It becomes 1 over 1. Yeah, it's weird. It's so weird. Oh my gosh, marker. If I had a 2 over 2, it simplifies to become 1 over 1. And that's exactly what I'm going to do right here. That is exactly what I am going to do right here. It's so weird, but I love it so much. Let's see what we got here. This 2 over 2, I zoomed in a little bit. There we go. Zoom out a little bit. Okay, good. Becomes a 1 over 1. Keep the negative on the bottom. You have to have a number in the bottom of that T-chart. And if it's 2 over 2 just simplifies to become a 1, I need you to think of it as a 2 over 1. As a result, vertically, in this T-chart, vertically, you get a 2x plus 5. And in the other half, this is no longer a 2x, this is a 1x. This is no longer a negative 2, this is a negative 1. This is a 1x minus 1. There are my factors. So it's interesting because I asked, did you guys see any fractions? And you were like, no. And then you were like, wait a minute. I kind of see a fraction, but no, that's just a T-chart. But no, I wanted you to think of that as a fraction. As long as you think of that as a fraction in the T-chart, you can simplify it. And if you can simplify, you must simplify. That's how this thing's going to work. Just as a side note, how do I know I'm right? Check it. You could check your work. I could check it by multiplying them back together. You know, again, this is not something that I would typically write. I'm gonna erase this in a moment. But I'm gonna check my work by simply multiplying these two things together. There's a 2x squared. There is 5x and a negative 2x make 3x minus 5. Nailed it. That's how you can check your work to make sure that you're correct. Oh, it's wonderful. The Tucker method. The Tucker method of ripping things apart. I love it. Let's try another one. Let's see here. Yes. Oh, yeah. I just have to, hold on a sec. Here, come here. Don't go in front of the camera, but fill this out real quick because I want to write the next example up there. Here, go write it in that. There you go. Okay. So, there we go. The next example that I have for you guys is this. There we go. Now, ladies and gentlemen. Oh, I'll take it. Oh, no, I was hoping you'd fill out everything else.
Oh.
I got it. It's fine. I was just hoping you'd fill out everything else. Because it's got to be that, and it's got to be that, and it's got to be that, and it's got to be... Oh, I would do that part, of course, and then it would be 1040. So, all right, we'll get there. What's so weird about this equation? Oh, no, there's the C. Ah, but wait a minute. Wait a minute. There's a B. Ooh, it's 0. 0's a number. 0 is an often neglected number. Neglected, sad. X squared minus 100. Technically, it is x squared plus 0x minus 100. And we got to factor it. So, GCF. What number's in front of this x squared? Yeah, it's a 1. So it's like 1 in 100. GCF is 1. Okay, screw that. Next step. Next step, I got to multiply A times C. So if I multiply A times C, I get negative 100. Good. All right. I need two numbers that multiply to negative 100, but at the exact same moment, they add up to 0. He just stole your thunder. But yeah, 10 and negative 10. You're trying to find two numbers that fit that multiplication and add up to the proper B value. They have to do both. That's what makes them magic numbers. T-chart, 10 and negative 10. X and X, a 1X and a 1X technically. Nothing simplifies. It becomes X plus 10, X minus 10. Here's a question that people typically throw at me. Mr. Markey, doesn't matter what order we write them in. It doesn't. Multiplication is what we call commutative. It doesn't matter what order we do it in. It doesn't matter if it's 10 times negative 10 or negative 10 times positive 10. It gets the same result. Same thing with these things right here. X plus 10, X minus 10. Furthermore, let me go back a page. Right here. Check this out. The commutative property. This could be 2x plus 5 times x minus 1, or this could be x minus 1, 2x plus 5. Either way works in terms of the commutative property of multiplication. His neck's going to hurt later. I think it's going to hurt later. Do you agree? I think it is. He's going to wake up with a sore neck, and he's going to stand up and stretch and go, "Ah!" Well, not really in an angry way, but more of a stretchy kind of way. Hey. Yeah? I was making sure you were okay. Yeah, I thought you died. Okay. If I died, would you save me? Interesting. If you can. All right. I think I said this like on day one, like there's going to be a day where I'm going to trip and fall and crack my head open, and you guys are going to be like, whoa, okay. No one saved me. They just kind of laughed a little bit. I've often wondered what would happen if there was an emergency in my classroom, how my students would react if I was like knocked out or something like that. Like, would somebody take the lead and be like, you, go to the next class and get a teacher. You, run to the main office and get security. Like just some junk like that. I was just wondering if anybody would ever take like leadership in that regard. But then I thought, no, most of them would just kind of sit there and panic and like take out their phones and videotape stuff. You know, this will make a great TikTok. Oh, wait, too soon? Is that going to be banned yet? It what? Would he be filming?
Yeah, he makes a TikTok out of it. He'd probably be dancing next to mommy.
Really? Nice. So
He's like kind of TikTok famous, like a little bit.
I don't care.
So like that's what I mean. Like he'll be making a lot of like videos, like constantly.
Just-
and taking it.
Of my dead body?
Yeah.
Okay.
See, that's immediately
Anyway, let's try another one. I'm ready to get on this page because I simply have the room for it. Ladies and gentlemen, give me a number. Okay. X squared plus 8x plus, no, not plus. Let's do minus. Minus, give me another number. 4. All right, let's factor that one. Can I take out a greatest common factor? Ooh, hold on a tick. Talk. See, I brought it all back. I said, hold on a tick. And then I said, talk. Because it was funny and hilarious. Ready? 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 Anyway. You would think 8 and 4. 8 and 4. You would think, oh, yeah, GCF, they have a 4. Nope. Nope. It has to be in common with all 3 terms. It has to be in common with all 3 terms. So, can't take out a GCF. What's A times C? What's A times C for this problem? -4. Okay, let's write it down. Hold on. Let me get there. A times C is -4. Cool. I need 2 numbers. Wait a minute. Wait a minute. Hey, just give me 2 numbers that multiply to -4. Any 2 numbers. 2 and -2. -2 and 2 is the same thing. Give me another pair. 4 and -1. Give me another pair.
1 and -4.
1 and -4. Is that it? Same thing. Same thing. Oh, man. Do any of them add up to 8? Oh, man. Oh, man, what do we do?
Make a new problem.
Unless this is the problem I wanted. Ladies and gentlemen, have we shown that no numbers that multiply to -4 work? Yeah, we've shown that every pair of numbers that multiply to -4 do not add up to 8. There's no other options. It's not factorable. What's an example of a number that is not factorable? Just any number that's not factorable? 7. Why 7? Which makes 7. Which makes 7. You said 7. You can't factor it, right? Which makes a 7.
Not factorable.
Wait.
I'm stuck on 7. I'm still on 7. So you said 7. I said, what number can you not factor? You said 7. I agree. It's not factorable. What special designation does 7 have? No, it is a prime number. A prime number is a number that you cannot factor. A prime number only technically has 2 factors, 1 and itself, which you can't do on a factor tree. Yeah. You know all your prime numbers to 100? 11's next, actually. Yeah. Was it 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31? I like to show off. I'm just saying, like, I can't, in my mind, I really don't even know if there are people here. You just might all be figments of my imagination, so I have to show off to somebody.
You know, sometimes I think that about the world. Like, you thought about like, what if we're all living in the simulation?
What if we're all what?
Like living in a simulation.
It's possible. It's possible.
What if we're
Yeah.
all just like in a pod?
It's possible. Here's the thing. There's only one thing, no matter what faith you come from, no matter what background you come from, no matter what belief structure you have, there's one thing that all human beings across the history of the universe can agree upon. And it's a simple philosophical statement. I think, therefore, I am. Which simply put means because I have the ability to have independent thought, I exist. And that's regardless of what faith you belong to, regardless of what country you come from, regardless of what background you have. That's one thing we can all agree on philosophically. I think, therefore, I am.
But if everybody thinks that, then why do you think that we're not real?
No. I'm real.
I know.
I don't know that you're real.
No, I know, but if I think the same thing.
But how do I know that it's not just my brain making your brain think that?
Is this still math though?
It's just.
Oh, my wife calls it motivational math with Mr. Markey.
I think it's
Don't tell me what I can do. You're a figment of my brain. I can tell you what to do. Okay, I got 2 examples for you. Ladies and gentlemen, every time I wake up in the morning, I think to myself, how can I collect the tears of my students in order for me to live forever? Oh, this is your first day. They've at least had like one other day with me. Oh, gosh. I have 2 problems that I want you to do. Now, I'm going to walk you through a tiny portion of one of them, but you are going to try both these problems on your own. But I'm going to walk you through the first step. First of all, first problem on the left. Boom. They both got a 4 in common, but not the 15. So I can't do GCF here. But the next one, they all do have a 4 in common. I like throwing things and punching things. Who in the what? No. That's not what I said. You can't do step 1 of the Tucker method. Step 1 of the Tucker method is to take out the GCF. Step 1 on the left problem, can't do it. But on the right problem, you can. And I told you I was going to do the first step with you, which means if I take out that 4, if I divide each of these terms by 4, I end up with this quadratic. Now, just for the sake of argument, what's step 2? A times C. But now here's the thing now. Where am I getting my A and my C for this problem? From the parentheses. Yes. When you do the A times C for this problem, you are doing your A times C based on what is inside of the parentheses. Keep that in mind. Ladies and gentlemen, I'm going to give you just a few minutes to get done both of these problems. Get them done now. I'll review them before we leave. Back in. There we go. There we go. when you do the magic numbers. You don't need to break it down all the way. You just need to break it down into two numbers, the two magic numbers that fit the criteria of multiplying and adding to that b value. So in reality, these two numbers might have worked, but these two numbers add up to -4. Put the negative on the 6. You don't have to do the rest of that number tree. What do you guys notice about the quadratic that's in the parentheses? Did anybody pick up on that? No. Not about the numbers and how to do the problem. Does it look familiar? What's inside of the parentheses? Does it look familiar? It's the first quadratic I wrote on the board today. Did any of you notice that? It's like I planned these things ahead. All right. Let's see what you got so far. Some of you are done. Some of you are finishing. It's okay. Let's see what we got. In the first problem, you could not take out a GCF. So instead, I did A times C. And I got -60. Ouch. That kind of sucks. Are there people laughing in my hallway? There's no laughing in my hallway. Anyway, -60. Man, you're telling me I got to find two numbers that multiply to -60 and add up to +4? What in the world? Is there any such numbers that exist? What? -6 and 10. Oh my. All right, -6 and 10. I can deal with that. T-chart. -6 and 10. What do I put in the top of the T-chart? 4x and 4x. Temporarily, I put a 4x and a 4x. The reason why it's temporary is because something is going to simplify in a little bit. It's going to simplify in a little bit. Where's my red pen? There's my red pen. If you hadn't already known, 4/6 reduces to 2/3. Keep the negative on the bottom. 4/6 reduces to 2/3. Keep the negative on the bottom. 4/10 reduces to become 2 and a 5. They both reduce. If you can reduce, you must reduce. All right. So what does this become? This becomes what? A 2x minus 3 and a 2x plus 5. Or if you went the other way around, it could be a 2x plus 5, 2x minus 3. It works all the same. But that's my answer. Hey, what was the only difference between these two problems in the very beginning? What was the only difference between these two original problems? Yes, but I mean, like, visually, what's the only difference between the two problems? 15 and 24. That's the only difference. 15 and 24. Let's see what happens with the next one. A times C was -6. I said we had to do A times C based on what was inside of the parentheses. This is a 1. My B value is a 1. And since my B value is a 1, 3 and negative 2 should work. Or negative 2 and positive 3. Either way it works. All right. T chart, 3 and negative 2. According to this, again, I'm only dealing with what's inside of the parentheses. So this is a 1x and a 1x. Nothing simplifies. This becomes x plus 3, x minus 2. But, however, whatever other English word can fit that phrasing. If you left it here, if you left it as x plus 3, x minus 2, I'm sorry, I'm going to mark it wrong. If you left it like this, I'm going to mark it wrong. Why? There again. The 4. Ladies and gentlemen, what have I been labeling these two terms as in other problems? I've been labeling them as the prime what? Prime factors. I've been labeling them as the prime factors. The whole point of today has been reintroducing you to factoring quadratics, getting quadratics down to their prime factors. You told me I forgot the 4. The 4 we took out at the beginning because this 4, the one that I'm pointing to right now, is the greatest common factor. It's a factor. It counts. It counts as a factor to the problem. And because it counts as a factor to the problem, I have to include it. The whole idea of factoring is ripping these things apart to their prime Legos. 4 counts. It does. Look how amazing this is, though. Look at this. Look how intriguing this is to me. This is very intriguing to me. This had a 15. This had a 24. Two numbers that are easily factorable. You could factor 15 and 24. Oh, happy day, la-di-da. But then because of that one tiny little change, look at the difference. Look at the difference in the answers. Such vast differences just by changing one number. That is the amazing thing about mathematics. Ladies and gentlemen, just a reminder, if you haven't gotten your online textbook, make sure you're following those directions. If you have any issues, make sure you email me. Make sure you are jumping on that benchmark. It is your read enrichment activity for the week. Make sure that you are on that for the benchmark. Get that thing done. Follow the directions. That would be wonderful. That is going to be due tomorrow. I need that done because my supervisor wants the data. Yeah. Anyway, I'm going to log off here. Thank you for joining us in the chat. I'll see you another time. I don't know. I don't really have a sign-off catchphrase. I need to have a sign-off catchphrase.